Hello there, and welcome to the Sleeping Physicist. If you're someone who likes to unwind by thinking about stars, particles, and the quiet structure beneath the universe, you're in the right place. Tonight, we'll let our attention drift gently into real physics and real discoveries. Some of what you'll hear may sound unfamiliar at first, but all of it is grounded in careful observation and well-tested theory. And if you enjoy these slow explorations, you're always welcome to like and subscribe. But for now, get comfortable, let your body rest, let your thoughts wander, and settle in with me. What is radiation actually made of according to quantum physics? Even before we try to answer that, radiation is already touching you. If there is a lamp nearby, light from it is reaching your eyes. If your room is warm, invisible radiation is flowing gently from walls, furniture, and your own skin. If you've ever stood in sunlight and felt its warmth settle on your face, you were feeling radiation directly, not as an idea, but as a physical exchange of energy. Radiation is not rare, distant, or exotic. It is one of the most common ways the universe communicates change from one place to another. When we observe radiation in the real world, what we notice first is not its composition, but its effects. Light illuminates, heat warms, sunlight powers photosynthesis and slowly fades paint. These effects happen without anything solid traveling from the source to you. No grains, no dust, no stream of matter crossing the space in between. Something leaves a hot object or a glowing surface, crosses empty space, and arrives carrying energy. That simple observation is where the question begins to take shape. At first glance, radiation feels almost like a message sent across distance. Something changes at the source, and later, something changes where it arrives. If you like, take a moment to notice where you're listening from right now. Perhaps a room, a bed, a quiet corner somewhere in the world, and recognize that radiation from distant stars has been passing through that space for billions of years, long before you arrived there. This is not poetic exaggeration, it is a measurable fact of the universe. The reason this matters is that radiation behaves consistently. It moves at a fixed speed in vacuum. It spreads outward from its source. It carries energy but no rest mass. These properties are not optional details. They are clues. They tell us that radiation is not made of the same things as air, dust, or atoms. Whatever radiation is, it follows different rules, and those rules point us toward a deeper structure underlying space itself. Once physicists accepted that radiation is something real moving through empty space, the next step became unavoidable. If radiation is not matter, but it still carries energy and momentum, then something fundamental must be oscillating, changing, or being excited as it travels. And that realization leads directly to the first major way humans tried to understand what radiation is made of at all. For a long time, the most natural way to describe radiation was to say that it is energy on the move. When something is hot, it loses energy. When something is illuminated, it gains energy. Radiation is the bridge between those two events, carrying energy across space without dragging matter along with it. This idea alone already separates radiation from anything solid or tangible. It does not pile up, it does not leave residue, and it does not slow down the way objects with mass do. What makes this idea powerful is that energy, in physics, is not a substance, it is a property. It describes the ability of a system to cause change. When radiation moves, nothing material is being transported in the usual sense. Instead, the state of space itself is changing from moment to moment in a very specific, organized way. Energy is not riding inside radiation like cargo. Energy is the motion. An intuitive way to picture this is to think of a calm lake. If you toss a stone into the water, ripples spread outward. The water itself does not travel across the lake. Individual water molecules mostly stay near where they started, yet energy moves outward in a clear, measurable pattern. Radiation, at first, seemed similar. Something at the source vibrates or oscillates, and that disturbance travels outward, carrying energy with it. This picture helped physicists make sense of many observations. It explained why radiation spreads out as it travels, why it can interfere with itself, and why it can pass through empty space. it also fit neatly with the idea that electric and magnetic effects are linked, changing together and sustaining one another as they move. Radiation appeared to be a self-propagating pattern, a kind of organized motion that did not need a material medium to exist. But there was a quiet tension hidden inside this explanation. If radiation is only a smooth, continuous flow of energy, then it should be able to deliver energy in arbitrarily small amounts. It should warm things gradually, continuously, without jumps or thresholds. Yet when physicists looked carefully at how radiation interacts with matter, especially at very small scales, nature did not behave that way. Energy did not always arrive smoothly. Sometimes it arrived all at once, or not at all. Certain interactions only happened if radiation carried enough energy in a single encounter. This was not a flaw in measurement. It was a pattern, repeated across experiments, and it suggested that describing radiation purely as flowing energy was incomplete. Something about radiation structure was being missed, and uncovering it would require letting go of the idea that energy always moves in a perfectly continuous way. To resolve that tension, physicists leaned more deeply into the idea of radiation as a wave. Not a wave made of matter, but a wave made of electric and magnetic change, endlessly regenerating itself as it moved. Electric field changing in time creates a magnetic field, and a changing magnetic field creates an electric one, and together they travel forward through space at a fixed speed. This was not speculation. It was written cleanly into the equations of electromagnetism and confirmed by countless experiments. In this picture, radiation is not something moving through space. It is something happening to space. At every point it passes, electric and magnetic fields rise and fall in a rhythmic pattern. The wave carries energy because changing fields store energy, and as the pattern propagates, that stored energy moves along with it. Nothing needs to be pushed ahead of it. The wave sustains itself. This explanation was remarkably successful. It predicted the speed of light exactly. It explained reflection, refraction, diffraction, and interference with stunning accuracy. It told us why different kinds of radiation exist, from radio waves to visible light to X-rays, all distinguished only by how rapidly their fields oscillate. For a time, it seemed that radiation had been fully understood. It was a continuous wave, smooth and unbroken, flowing through space like a perfectly elastic vibration. If you imagine a stretched rope being shaken up and down, the shape of the wave can be gentle or tight, slow or rapid, but it remains continuous along its length. At any point, you can always find a smaller motion within a larger one. The wave picture of radiation worked the same way. Energy could be spread thinner or thicker, but it was never fundamentally divided. Yet this elegance carried a quiet assumption. If radiation is truly continuous, then any interaction with matter should be divisible without limit. Atoms should be able to absorb just a fraction of a wave's energy, or release energy smoothly back into the field. But when physicists began examining radiation at the scale of individual atoms, that assumption began to crack. Atoms did not respond gradually. They jumped. They absorbed radiation only at specific energies. They emitted radiation in sharp lines, not smooth bands. The wave picture could describe how radiation traveled, but it could not explain how radiation was exchanged. And because measurement always involves interaction, this flaw could not be ignored. What this revealed was subtle but profound. The wave model described radiation's motion through space beautifully, but it failed to describe radiation's structure when it met matter. Something about radiation itself was not as smooth as the wave suggested, and it was precisely this failure that forced physics to take its next irreversible step. The first cracks appeared when physicists tried to understand how hot objects glow. As something is heated, it emits radiation, and the color and intensity of that glow change in a very precise way. Classical wave theory predicted that a hot object should emit enormous amounts of high-frequency radiation, far more than was ever observed. According to the equations, the energy should rise without limit as the waves became shorter and more rapid. In reality, it didn't. The glow peaked, then faded. Nature applied a cutoff where theory said none should exist. This mismatch was not small, it was catastrophic. The predictions diverged wildly from experiment, and no adjustment to the wave model could fix it without breaking everything else that worked. The problem became known as the ultraviolet catastrophe, not because it was dramatic, but because it exposed a fundamental misunderstanding. Radiation was refusing to behave like a smooth, continuous wave when energy exchange was involved. A second, even more unsettling problem came from shining light onto metal surfaces. When light hits certain metals, electrons can be ejected, but only if the light has a high enough frequency. Brightness alone does not matter. You can increase the intensity of low-frequency light indefinitely and nothing happens, but a dim beam of higher frequency light can instantly knock electrons free. This made no sense in a purely wave-based picture. If radiation were just a continuous wave delivering energy gradually, electrons should respond slowly, accumulating energy over time until they escaped. But they didn't. They responded immediately, or not at all. Each interaction seemed to involve a specific, indivisible amount of energy. Radiation was arriving in discrete events, not as a smear. These experiments were not edge cases, they were simple, repeatable, and unavoidable. Radiation was interacting with matter as if it were made of units, not a continuous flow. And yet, when radiation traveled through space, it still spread and interfered exactly like a wave. The contradiction was no longer theoretical. It was sitting on laboratory tables all over the world. What physicists were forced to accept was that radiation could not be fully described by any single classical picture. It was neither just a wave nor just something else. Entirely. The structure of radiation itself had to be reconsidered, not as a failure of measurement, but as a clue. And that clue pointed toward a new idea that would permanently change what it means for something to exist in the universe at all. The solution began with a quiet but radical proposal. Instead of assuming that radiation could carry any amount of energy smoothly, physicists considered the possibility that energy exchange itself might be limited to specific amounts. Not because of technological limits, but because nature itself was structured that way. Radiation, when emitted or absorbed, might do so in discrete steps. This idea did not begin as a declaration about reality. It began as a mathematical repair. By assuming that energy could only be emitted in fixed portions, the predictions for glowing objects suddenly matched observation perfectly. The runaway excess at high frequencies disappeared. The glow of hot matter made sense again. What had looked like a bookkeeping trick turned out to be a window into something deeper. The crucial shift was realizing that radiation does not deliver energy continuously when it interacts. Instead, it exchanges energy in indivisible events. Each event has a size set by the radiation's frequency. Higher frequency radiation delivers larger packets of energy. Lower frequency radiation delivers smaller ones. This immediately explained why brightness alone could not eject electrons from metal. If each packet was too small, no amount of accumulation could help. The interaction simply would not occur. An intuitive way to think about this is rainfall. A steady drizzle and a downpour may deliver the same total amount of water over time, but if each drop is too small to trigger a mechanism, nothing happens. It is not the flow that matters, but the size of the individual drops. Radiation, in its interactions, behaves like that. The energy arrives not as a mist, but as distinct impacts. What made this insight extraordinary is that it did not replace the wave picture. Radiation still spread like a wave. It still interfered and diffracted. But when it met matter, it behaved as though its energy were bundled into discrete units. The wave described how radiation moved. The packets described how radiation acted. At this point, the question of what radiation is made of could no longer be avoided. If radiation exchanges energy in individual units, then those units must correspond to something real, not metaphorical. They were not pieces of matter, but they were not mere accounting tools either. They were the first glimpse of radiation's quantum structure, and they demanded a name, a definition, and a place within the physical fabric of the universe. Those discrete units of radiation came to be called photons, but the word itself can be misleading if taken too literally. A photon is not a tiny glowing marble flying through space, and it is not a miniature bullet of light. It has no surface, no internal structure, no size you could point to. Trying to imagine a photon as a small object almost immediately leads to confusion, because photons do not behave like objects made of matter. What a photon represents is a single, indivisible exchange of energy between radiation and matter. It is the smallest possible interaction allowed at a given frequency. When an atom emits light, it does not release a fraction of a photon. When an electron absorbs light, it does not take half of one. The interaction happens whole, or not at all. The photon is the event itself, not a container carrying something inside it. This distinction matters. Radiation does not consist of photons in the way a gas consists of molecules. Instead, photons appear when radiation interacts. They mark the moments when energy is transferred, measured, or absorbed. Between those interactions, radiation still spreads through space as a wave, extended and delocalized, not pinned to a single point. An analogy that helps here is a vibrating string connected to a bell. The vibration can spread smoothly along the string, but the bell only rings when it receives enough motion in one moment to trigger it. The ringing is discrete, even though the vibration is continuous. The photon is like the ringing, not the vibration itself. It is the quantized response, not the medium. This is why photons can seem to appear in one place and disappear in another without traveling as tiny objects in between. The underlying electromagnetic field exists everywhere. Radiation is a pattern in that field. A photon is what we call the smallest possible disturbance of that pattern when it exchanges energy with matter. Understanding this removes a great deal of confusion. Radiation is not made of little particles flying through empty space, but neither is it a purely abstract wave. It is something deeper, something that behaves like a wave while it propagates and reveals its quantized nature only when interaction forces the universe to choose a definite outcome. This dual behavior becomes unavoidable when we look at how radiation spreads versus how it interacts. When radiation travels freely through space, it does not choose a single path. It spreads out. It bends around obstacles. It overlaps with itself and creates interference patterns that can only be explained by waves occupying many places at once. No single trajectory can describe that motion. Radiation behaves as though it is extended, distributed, and everywhere the wave allows it to be. Yet the moment radiation meets matter, that extended pattern resolves into a single localized exchange. An electron absorbs one photon at one place. A detector clicks once. A molecule changes state in a specific location. The wave does not partially interact in many places. The interaction is singular. This is not a switch between two different kinds of things. It is one underlying reality, revealing different aspects depending on what is happening. What this tells us is that wave and particle are not competing descriptions. They are incomplete perspectives. The wave description tells us how radiation evolves in space and time when it is not being measured. The particle description tells us how radiation exchanges energy when an interaction forces a definite outcome. Neither can be removed without breaking the theory. A helpful way to think about this is to imagine a cloud passing overhead. The cloud is spread out, soft-edged, and extended across the sky. But when rain falls, each drop lands in a specific place. The drop is not a tiny cloud, and the cloud is not made of falling drops until interaction occurs. Radiation behaves similarly. Its spread is wave-like. Its impacts are discrete. This duality is not a failure of understanding. It is a precise description of how nature behaves. Quantum physics does not say that radiation is sometimes a wave and sometimes a particle. It says that radiation is something deeper than either concept, something that produces wave-like evolution and particle-like interactions as natural consequences of the same underlying structure. Once this is accepted, the question shifts again. If photons are not tiny objects and waves are not material substances, then what is the thing underneath that gives rise to both behaviors? Answering that requires stepping back one more level, beyond particles and waves entirely, and looking at what quantum physics says space itself is filled with. At the deepest level we currently understand, radiation is not built from particles or waves, but from fields. According to quantum physics, space is not empty, even when nothing obvious is happening in it. Every point in space is permeated by an electromagnetic field, a real physical entity that can exist, fluctuate, and store energy even in complete darkness. Radiation appears when this field is disturbed in a particular way. A vibrating charge, such as an electron in an atom, sets the electromagnetic field into motion. That motion spreads outward, not because something is traveling through space, but because the field itself is changing from point to point. Radiation is the organized propagation of that change. In this view, photons are not objects moving through space. They are the smallest possible excitations of the electromagnetic field. When the field is excited gently, it corresponds to low-frequency radiation. When it is excited more sharply, it corresponds to higher frequency radiation. The field does not break into pieces. It responds in quantized steps because that is how quantum fields are structured. An analogy that helps here is a calm, stretched fabric. You can pluck it softly or sharply, creating different patterns of motion across its surface. The ripples are not separate things riding on the fabric. They are what the fabric is doing. In quantum physics, the electromagnetic field is the fabric, and radiation is its motion. This perspective explains why radiation can exist without matter, why it travels at a fixed speed, and why its energy comes in discrete amounts when measured. The field exists everywhere, even in regions where no photons are detected. Photons appear only when the field interacts with something else, when energy must be exchanged in a definite way. Once radiation is understood as a field phenomenon, many apparent contradictions dissolve. There is no need to ask whether radiation is a wave or a particle. It is neither and both, because those are emergent descriptions of a deeper field-based reality. And with that understanding in place, the final piece of the puzzle becomes clear when we look at how radiation actually makes itself known to us at all. Radiation becomes meaningful to us only when it interacts. Until that moment, it can pass silently through space, carrying energy without leaving a trace. Detection happens when radiation meets matter, and the electromagnetic field couples to charged particles, usually electrons bound inside atoms. This interaction is where the abstract becomes tangible. When radiation reaches an atom, the electromagnetic field begins to influence the electron's motion. But the electron cannot respond arbitrarily. It occupies specific energy states, and it can only move between them in discrete jumps. If the radiation carries exactly the right amount of energy in a single quantum, the electron absorbs it and transitions to a higher state. If not, nothing happens at all. This selectivity is not a limitation of atoms. It is a reflection of the quantum structure shared by both matter and radiation. This is why radiation leaves such precise fingerprints. Spectral lines, detector clicks, chemical reactions, and even vision itself depend on these quantized exchanges. In your eyes, photons trigger molecular changes in retinal cells. Each change begins with a single, indivisible interaction between radiation and matter. Brightness increases the number of interactions, not their size. Color reflects the energy of each one. An intuitive way to picture this is to imagine a staircase rather than a ramp. You can stand on one step or the next, but not in between. Radiation does not push electrons smoothly up a slope. It lifts them step by step, or not at all. The steps belong to the atom, the lift belongs to the radiation, and the fit between them determines whether an interaction can occur. Through these interactions, radiation becomes measurable, useful, and transformative. It heats planets, drives chemistry, carries information, and reveals the structure of distant stars. But none of these effects require radiation to be made of matter. They require only that the electromagnetic field can exchange energy with matter in quantized, rule-governed ways. And that brings us to the final clarity the question has been moving toward from the beginning. When all of these pieces are placed together, the answer becomes unexpectedly simple. Radiation is not made of matter, and it is not made of particles in the ordinary sense. According to quantum physics, radiation is made of excitations of a field that exist everywhere in space. It is the electromagnetic field itself, changing in time and carrying energy through its motion. When radiation travels freely, it does so as a wave-like evolution of that field, spread out and delocalized, obeying precise laws that determine how it propagates. Nothing needs to be counted or tracked as an object during this motion. The field alone is sufficient. But when radiation interacts, when energy must be transferred to or from matter, that same field reveals its quantized nature. The exchange happens in discrete units, which we call photons. Photons are not building blocks stacked together to make radiation. They are the smallest possible outcomes of interaction. They are how the universe keeps its accounting consistent when energy moves between fields and particles. Radiation itself exists whether or not photons are observed. The field does not turn on and off. Only our access to its energy does. This is why the question feels subtle. Asking what radiation is made of assumes it must be made of something like matter is. Quantum physics gently dissolves that assumption. Radiation is not a thing traveling through space. It is a process occurring within space. It is what the electromagnetic field does when it is set in motion, and photons are how that motion becomes visible to matter like us. Once this is understood, the behavior of radiation no longer feels contradictory. Its wave nature and its particle-like interactions are not competing explanations. They are complementary expressions of a deeper field-based reality. Radiation is coherent, structured, and real, not because it is made of pieces, but because the laws governing fields are precise and universal. And with that clarity, the original question quietly answers itself. Radiation is made of quantized field excitations, emerging only when interaction demands it, and otherwise existing as a continuous dynamic presence woven into the fabric of space itself. Once radiation is understood as activity within a field rather than a stream of objects, it becomes easier to notice something subtle but profound. Radiation is not only something emitted by stars, lamps, or hot surfaces. It is a constant, quiet presence woven throughout the universe. Even in regions far from galaxies, even in the deepest cosmic voids, the electromagnetic field is never perfectly still. Space itself carries a faint afterglow from the early universe, a bath of low-energy radiation left over from a time when matter and radiation were tightly coupled everywhere. This radiation does not rush or blaze. It simply exists, filling space uniformly, its field gently fluctuating at every point. It is not waiting to be used. It is already there, part of the universe's baseline condition. What makes this remarkable is that radiation does not require intention or structure to persist. Once the electromagnetic field is excited, it continues according to immutable laws. No memory, no guidance, no direction is needed. The field evolves smoothly, and energy flows where the equations allow. Radiation is not purposeful, yet it is extraordinarily reliable. It arrives from distant stars with information intact after traveling for millions or billions of years. This reliability is why radiation becomes one of our most trusted messengers. When we observe light from a distant galaxy, we are not catching particles that have survived a long journey. We are witnessing a field pattern that has evolved coherently across vast stretches of space and time. The radiation is not aged or worn. It is simply the electromagnetic field doing what it always does. Seen this way, radiation is less like an emission and more like a conversation already in progress. Matter speaks by disturbing the field. Space listens by carrying that disturbance forward. Matter elsewhere responds if the exchange is allowed. Nothing extra is required. The universe is already set up for this exchange to happen, quietly and continuously, without effort or intention. Even when radiation is not being emitted or absorbed, the electromagnetic field is never perfectly quiet. Quantum physics tells us that fields cannot be completely still. They possess a baseline activity, a subtle restlessness, that persists even in what we would otherwise call empty space. This is not noise or chaos, but a consequence of how quantum systems are structured at the deepest level. The field can never be pinned to an exact value everywhere at once. There is always a small, unavoidable fluctuation, a gentle trembling built into the fabric of space itself. These fluctuations are not photons in the usual sense. They do not carry energy that can be harvested or detected directly, but they shape how radiation behaves, how atoms interact, and how forces operate across distance. An intuitive way to picture this is to imagine a perfectly calm sea that still has microscopic ripples across its surface. From far away it appears flat, but at close range it is alive with motion. The electromagnetic field behaves similarly. Even in the absence of visible radiation, it remains an active participant in the universe's dynamics. This ever-present field activity means radiation is not an isolated phenomenon that switches on and off. It is an expression of a deeper continuity. When a star ignites, it does not create the field, it excites what is already there. When radiation fades into space, it does not disappear into nothingness. It becomes part of the ongoing evolution of the field. This perspective quietly reshapes the original question. Radiation is not something the universe occasionally produces. It is something the universe is already prepared for, everywhere, at all times. The electromagnetic field is the stage, and radiation is what happens when that stage is set into motion, following rules so consistent that calm emerges naturally from their precision. And if you'd like to continue exploring further layers of this idea, from how radiation relates to time itself to how quantum fields connect all forces, we can simply keep going. One of the quiet consequences of radiation being a field process rather than a moving object is how deeply it is tied to time itself. Radiation does not exist without change. A perfectly frozen universe, one in which nothing evolves, could not contain radiation at all. Radiation is the record of change propagating forward, the electromagnetic field responding moment by moment to what has already happened. When a charge accelerates, radiation is produced. That acceleration is a change in time, not just in space. The field responds to that change and carries its influence outward. This means radiation always points away from its cause. It never arrives before it is emitted. It never runs backward. Radiation carries an arrow of time embedded in its very existence. This is why radiation is such a reliable storyteller of the past. Light reaching your eyes from a distant star is not showing you the star as it is now, but as it was when the field was last disturbed in that way. Radiation does not update itself. Once the electromagnetic field begins evolving outward from an event, it carries that information forward faithfully, without revision. An intuitive way to think about this is to imagine ripples spreading across water after a stone is dropped. The ripples encode the moment of impact, even long after the stone has sunk. Radiation does the same thing, but across space and time together. The electromagnetic field remembers disturbances by continuing to evolve from them. Because of this, radiation is inseparable from causality. It ensures that influences propagate in an orderly way, that effects follow causes, and that the universe remains predictable at large scales. The quantum nature of radiation does not break this order. It preserves it. Quantization determines how interactions occur, but the field's evolution still respects the deep structure of time. Seen this way, radiation is not only energy in motion, it is history in motion. It is how events leave traces that can be encountered elsewhere, later. And this makes radiation not just a physical phenomenon, but one of the universe's most fundamental ways of keeping itself connected across distance and duration. When radiation is understood as a field evolving through time, its role in the universe begins to feel less like transport and more like connection. Nothing material needs to cross the distance between a source and an observer for influence to be felt. What changes instead is the state of the electromagnetic field linking them, already present at both locations. This means radiation does not bridge gaps by moving through emptiness. The bridge already exists. Radiation is simply the way a change at one place becomes a change elsewhere, following the field's rules. The universe does not send messages by throwing things across space. It reshapes itself locally, and those reshaped conditions propagate onward. An intuitive way to see this is to imagine a long line of gently touching dominoes, not falling, but flexible. Pressing one does not launch an object down the line. It changes the shape of its neighbor, which changes the next, and so on. Radiation works similarly, except the medium is not a line or a surface. It is space itself, permeated by field. This perspective helps explain why radiation can pass through vast emptiness without fading in purpose. It does not rely on endurance, it relies on continuity. As long as the field exists and the laws governing it remain unchanged, radiation remains faithful to its origin. Distance does not weaken meaning, it only delays arrival. Seen this way, radiation is not something added to the universe. It is one of the ways the universe expresses coherence across separation. It allows distant regions to remain part of a single unfolding reality, connected not by objects exchanged, but by lawful change carried forward through time. And from here, if you'd like, we can continue even deeper into how this same field-based picture extends beyond radiation itself, shaping our understanding of particles, forces, and the quiet unity underlying everything we observe. Once radiation is understood as the behavior of a field, it becomes clear that it is not an isolated case. Quantum physics treats every fundamental force in a similar way. Just as radiation arises from excitations of the electromagnetic field, other forces arise from their own fields, each filling all of space, each capable of being disturbed, each capable of carrying influence without transporting matter. This reframes radiation as part of a broader pattern rather than an exception. The universe is not built from particles first, with fields added later as explanations. The fields come first. Particles, interactions, and forces emerge from how those fields behave under specific conditions. Radiation is simply the most familiar example because it interacts so readily with our senses. In this view, the distinction between something and nothing becomes softer. Empty space is not an inert backdrop. It is active, structured, and responsive. When radiation passes through what we call a vacuum, it is not crossing a void. It is moving through a fully present physical system that happens not to contain matter. The electromagnetic field does not switch off just because atoms are absent. This is why the same principles that explain light from a candle also explain radiation from distant quasars and faint signals left over from the early universe. The scale changes, the energy changes, but the underlying reality does not. Radiation always emerges from the same field, obeying the same rules, no matter where or when it appears. Seen this way, radiation becomes a kind of unifying thread. It links small-scale atomic transitions to the largest observable structures in the cosmos. It connects the behavior of electrons in your eyes to processes that unfolded billions of years ago, not by carrying objects across space, but by letting the universe remain dynamically whole, moment to moment, through fields that never truly rest. And from here, if you'd like to keep going, we can continue outward again into how this field-based picture reshapes our intuition about emptiness, presence, and what it really means for something to exist at all. As the field-based picture settles in, it gently reshapes what emptiness means. What we call empty space is not a blank container waiting to be filled. It is already occupied by fields with structure, rules, and activity. Radiation does not invade emptiness. It reveals what emptiness already contains. When no light is visible and no heat is felt, the electromagnetic field is still present, defined at every point, capable of being excited. Radiation becomes possible not because something is added to space, but because space itself is responsive. The universe does not need to create a pathway for radiation. The pathway is built into its very fabric. This is why radiation can appear suddenly when conditions allow. An atom shifts state, a charge accelerates, a temperature changes, and the field responds immediately. Nothing needs to be assembled. Nothing needs to be launched. The response unfolds naturally, as a continuation of what space already is. An intuitive way to think about this is to imagine silence in a concert hall. The silence is not the absence of air. It is air at rest, ready to carry sound the moment a vibration occurs. Radiation is similar. Darkness is not the absence of the electromagnetic field. It is the field unexcited, waiting without effort. This understanding removes any sense that radiation is foreign or intrusive. It is not something that disrupts space. It is something space does. And because the field exists everywhere, radiation can connect distant regions without ever needing to cross a true void. The universe remains continuous, responsive, and quietly unified. From here, the question of what radiation is made of feels almost inverted. Radiation is not made of something placed into space. It is made of space behaving according to its deepest rules. And that realization opens a final, subtle layer of calm clarity, where existence itself begins to feel less fragmented and more coherent, moment by moment, everywhere at once. There is a calm consistency hidden inside all of this. Once radiation is understood as the electromagnetic field evolving according to fixed rules, it becomes clear why the universe feels so stable across time and distance. The same radiation that warms your skin behaves identically around distant stars. The same field equations apply in every direction, in every era we can observe. Nothing special has to happen for this consistency to hold. It is simply how reality is structured. Radiation does not need supervision. It does not adapt or decide. When a disturbance occurs, the field responds, and that response unfolds predictably. This predictability is what allows physics to exist at all. It is why we can trace light back to its source, why astronomy works, why the universe does not dissolve into randomness. Radiation is one of the clearest expressions of lawfulness made visible. What is striking is that this lawfulness does not feel rigid. It allows for endless variation. Different frequencies, intensities, directions and interactions all arise from the same underlying field. Complexity emerges not from different ingredients, but from different patterns of excitation. Radiation shows how richness can arise from simplicity without conflict. An intuitive way to feel this is to imagine a musical instrument capable of infinite melodies. The instrument itself does not change. The strings, the air, the structure remain the same. What changes is how it is played. Radiation is like that. The electromagnetic field is the instrument. The universe plays it endlessly, producing warmth, light, structure, and information without ever needing new material. This perspective carries a quiet reassurance. The universe is not fragile at its foundations. Radiation does not rely on delicate arrangements that could easily fail. It rests on principles so deep and uniform that they persist across billions of years. Every photon absorbed, every wave propagated, every interaction completed is another small confirmation that the same rules are still holding. And if you'd like, we can continue from here into how this deep consistency shapes our sense of presence, observation, and what it means to be part of a universe that communicates through fields rather than things. At this point, radiation begins to feel less like something happening out there and more like something we are quietly immersed in. Every act of observation you have ever made using your eyes depended on radiation interacting with matter inside your body. Vision itself is not passive. It is a continuous exchange between the electromagnetic field and the delicate structure of living cells. When light enters your eyes, it does not arrive as an image. It arrives as quantized interactions, individual exchanges of energy that trigger molecular changes. Your experience of a smooth, continuous world is built from countless discrete events stitched together by biology. Radiation makes perception possible, not by carrying pictures, but by enabling structured interaction. This means you are not separate from radiation as an observer standing apart. You are part of the same field-based reality responding to itself. The electromagnetic field evolves. Matter responds. Information emerges. Observation is not something added on top of physics. It is physics unfolding through specific arrangements of matter capable of responding to radiation. An intuitive way to think about this is to imagine a lake reflecting the sky. The reflection is not something placed on the water. It arises because of how the surface responds to light. Likewise, your awareness of the universe arises because your body is tuned to the field's behavior. Radiation does not merely inform you about the world, it participates in making experience possible at all. Seen this way, radiation quietly links the external universe to inner experience without crossing any philosophical boundary. It is simply interaction following rules. Stars shine, fields evolve, matter responds. Awareness arises as part of that chain. No extra ingredients are required. And so radiation, which began as a question about composition, gently resolves into a question about relationships. It is not made of substance in the usual sense. It is made of lawful change, shared everywhere, connecting events across space and time, and allowing a universe full of structure to be known from within. As this picture settles, radiation no longer feels like an object to be identified, but like a quiet language the universe uses to remain coherent with itself. Every time the electromagnetic field changes, that change carries structure, not intention, not meaning, but form. Radiation is how form persists beyond its point of origin. A star does not send out matter to announce its existence. It disturbs the field, and that disturbance carries the imprint of the star's temperature, composition, and motion. By the time that radiation arrives somewhere else, perhaps at a telescope, perhaps at a living eye, the field still carries those constraints faithfully. Radiation does not invent information. It preserves it. This is why radiation can feel so gentle and yet so powerful. It does not force contact. It does not require collision. It simply allows distant regions of the universe to remain informed about one another. The field evolves, and that evolution maintains correlation across space. The universe stays in conversation with itself, softly, continuously. An intuitive way to sense this is to imagine a vast room where a single tone is played. The sound does not push the walls outward. It fills the room by shaping the air everywhere at once as it travels. Radiation fills the universe in a similar way, shaping the electromagnetic field so that distant places are never truly isolated from the events that came before them. In this sense, radiation is neither substance nor signal alone. It is continuity. It ensures that causes do not vanish into silence, but leave traces that can be encountered later. Without radiation, the universe would still exist, but it would be opaque to itself, fragmented into isolated moments with no way to relate. And so the question that began with composition settles into a deeper clarity. Radiation is made of the same thing space is made of when space is allowed to change. It is the electromagnetic field in motion, structured by quantum rules, carrying energy and history forward without effort, without urgency, simply because that is how reality remains whole. By now, nothing new needs to be added for the picture to hold together. Radiation does not require hidden mechanisms or extra ingredients waiting offstage. It is complete in the sense that its behavior follows inevitably from what space is allowed to do. Once fields exist, once they can change, once quantum rules govern how energy is exchanged, radiation follows without exception. This completeness is what gives radiation its quiet elegance. There is no special case where it must behave differently. There is no boundary where it suddenly becomes something else. From the faintest microwave background filling the universe to the sharpest gamma ray burst, the same field is at work, responding to disturbances with the same steady discipline. What feels calming about this is that nothing is arbitrary. Radiation is not an accident layered on top of reality. It is an expression of the simplest possible requirement for a connected universe. If space can change, and if those changes must propagate, then radiation is unavoidable. It is not optional. It is built in. An intuitive way to rest with this idea is to imagine a universe where nothing could carry influence forward. Every event would be isolated, sealed into its own moment. Radiation prevents that isolation. It allows the universe to remain continuous with itself, not by force, but by structure. The field evolves, and the story continues, and so, without needing to conclude or summarize, the question rests naturally. Radiation is not made of pieces, nor of particles, nor of matter disguised as light. It is made of lawful change in a field that exists everywhere, shaped by quantum limits, carrying energy and history forward simply because space itself allows it to do so. If you'd like to continue, we can keep following this thread wherever it leads next, without urgency, letting the physics guide the next step as it always has. So the question can finally rest, not because it has been exhausted, but because it has been gently resolved. Radiation, according to quantum physics, is not a substance moving through space, and it is not a collection of tiny objects flying from place to place. It is the electromagnetic field itself, already present everywhere, responding to change and carrying that change forward in a lawful way. What we call photons are not ingredients mixed together to form radiation. They are the moments when that field is required to exchange energy in a definite, indivisible way. They are the punctuation marks, not the sentence. The sentence is the continuous, evolving field, shaped by quantum rules that limit how interaction can occur. Seen this way, radiation no longer feels mysterious or fragmented. Its wave-like spread, its particle-like interactions, its ability to carry energy, information and history across unimaginable distances all arise from the same simple foundation. Space is not empty. Fields exist. Change propagates. Energy is exchanged in quanta. Nothing more is needed. There is a kind of calm in realizing this. The universe does not rely on fragile mechanisms or hidden structures to remain connected. Radiation is not an exception or an add-on. It is an inevitable expression of a universe where space is active and rules are consistent. Light, warmth, and the faint afterglow of the early cosmos are all manifestations of the same quiet principle at work. And so radiation turns out to be made of something surprisingly gentle, not matter, not pieces, but the steady, lawful motion of a field that never truly rests, allowing the universe to remain whole, moment by moment, across space and time.